So we have an example here that the national study finds that college students with jobs worked an average of 22 hours per week. So that gives us our mu value of 22. And the standard deviation is 9 hours. That gives us our sigma of 9. A college student is randomly selected. Find the probability that the student works for less than 4 hours per week. So what we want is the probability that the random variable x of how many hours per week they work is less than 4. Notice this is continuous. It could be 3.5, it could be 2.5, it could be 2. It's not just stuck to being 0, 1, 2, 3, or 4. This is not discrete. Assume that the lengths of times that college students work are normally distributed. Normally distributed, all that tells us is that we can draw a bell curve. This is a symmetric and are represented by the variable x. Good. So I know it's normally distributed, so I'm going to go in and draw a bell-shaped curve. And I also know that in the middle of my bell-shaped curve needs to be my average of mu, which is 22. Okay. I'm going to start putting some other tick marks in here, moving to the right and moving to the left. And I'm just going to go by 6s. So I'll say that this is 20, and it's not terribly important what you go by, but just to make things a little bit easier, I'll say that's 28, and then I'll say that this is 34, and then going by 6s to the left, I will say that this is 16, and then I'll say that this is 10, so down here is 4, and then up here would be 40. Okay, so that's what our bell curve looks like. I'm going to see if I can move this top piece up a bit. Perfect. That's better because it never really hits the x-axis, right? And it'll give me some space to move. What we are interested in is the probability that x is less than 4. We want this area, this tiny little area off to the left of 4. That area that I shaded in red, that's the area that we want. Okay. Now remember, the issue is if this were z-scores, we would know how to compute this, but this is not a z-score, so we do not necessarily know how to compute this. But what we just saw earlier is that I can standardize this table. It's probably a little bit too big. I can standardize this table and draw a standard normal curve where now the mean mu in the standard normal curve would be 0. I'm moving by standard deviations of 1 in the standard normal curve. So on and so forth. Please, 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 everybody, do not think that this 4 has anything to do with that -4, okay? These are two completely different curves. The point is that whatever where that 4 lands, I'm just going to try to drop this down. And I'm not necessarily saying that this will be the z-score. I don't know exactly what the z-score will be, but somewhere this 4 corresponds to one of these z-scores. Somewhere over here. It might be over here, and I'm finding this area over there. It might be, say, right there. I lost my curve. That happens sometimes. But what we need to do, the point is, we need to find what is the z-score that corresponds to 4. The same way that up here, we found the z-score that corresponded to 600 was 1, we need to find what is the z-score that corresponds to 4. That's what we need right now. And we do know, we learned the formula earlier in this course, and we saw it again in lesson 14, that z is equal to x minus mu divided by sigma. So I'm looking for the z-score for the x value of 4 minus, I know mu is 22, and I also know that sigma is 9. I knew all of those. So 4 minus 22 gives me a -8, and -8 divided by 9 gives me -2. So now I know for a fact that this x value of 4 corresponds to the z-score of -2. So whatever that red area is off to the left is the same as this red area here, because the x value of 4 and the z-score of -2 match up. They correspond. And I know the areas don't look like they're the same. Like the one at the bottom looks a lot bigger, but it's just not drawn to scale. Okay, those areas are the same. So if what we wanted originally was p of x less than 4, remember the problem is we didn't have a way to do that because we only have a standard normal table. We have now converted that into the probability that z is less than -2. And this we learned how to compute in lesson 14. We could then compute that with our table, where we then go to our table and look for z-scores that are look for the area to the left of -2. We could go to StatCrunch, or we could pull up our calculator and do it that way. I think for this one, I'll just pull up my calculator here. So I'm going to hit clear on my calculator. I'm going to go to distribution. I want to go to normal CDF. My lower limit here is really, really small, so I'll just put -1000 because it doesn't have a lower bound. The upper limit is -2. And I am using the standard normal distribution, so I'll just keep those as 0 and 1, and I get about 0.0228 when I round that in my calculator. This is approximately 0.0228. So it's about a 2.28% chance that a student works less than 4 hours per week. And I think I'll also go into StatCrunch and show you all how you can get that answer on StatCrunch. So if you're doing this in StatCrunch, you will go to Stat, you'll open up Calculators, and you'll go down to, make sure everyone can see this, you'll go down to Calculators and then Normal. Keep your mean as 0 and your standard deviation as 1, but we want the probability that z was less than -2, so I'm going to hit less than -2, and I'm going to click compute, and I can see that I still do get 0.0228 after rounding, so that is the same thing. Okay, I want to show you something that you could also use StatCrunch to check this originally. If the mean of the original problem was 22, the standard deviation of the original problem was 9, and the original x value that we were working with is 4, we should get the exact same thing here, and we do. So this shows you what I've just shown you now is that these two pictures really do have the same red area shown to the left, whether you think of it as x values or whether you think of it as z values.